Here I have a pot of boiling water on an induction stove. Notice that there's a newspaper between the pan of boiling water and the burner, and the newspaper does not catch on fire. Also notice that the surface of the stove is very flat, that the burners aren't embedded into the stove. If I were to examine what is inside of one of these burners, I would find a coil of wire. So how does this stove work? If I take a piece of wire and I induce a current in this wire, an interesting thing happens. A magnetic field develops around this wire. And this magnetic field will affect any magnetic material. For example, if I were to put a compass near this wire, the compass needle would change direction. Now the needle in the compass is just a little magnet. It's a magnetic material. So this magnetic field that I create in this wire by running a current changes the direction of the compass. For example, if I reverse the direction of the current, say I run the current this direction in the wire, the magnetic field will change, it'll reverse, and the compass needle will point in a different direction. Perhaps it'll point down this way. So if I rapidly change the current in this wire back and forth, I can make this compass go crazy. I can have it jitter, jatter all over the place. And when I do that, I'm transferring energy to this compass needle. Now a similar thing happens when we use induction cooking. Instead of using a straight wire, I can make a coil wire like the induction burner. And like the straight wire, I can induce a current to flow in this coil back and forth. As I do that, let's examine what is happening in the cross section on the left side of the coil. Let's presume at an instant in time the current is flowing this way around the coil. And I want to look at these three wire cross section. So I'll see three wires closely packed together. Now the magnetic field in a single wire would just loop around the single wire, but when I put three wires together, the magnetic field changes. In this case, the magnetic field becomes counterclockwise around this loop. So the magnetic field will be in this direction. Now notice that in the cross section of the three wires at the right, the current is going in the opposite direction. So in these three wires, the magnetic field will be reversed. It'll go clockwise. It'll go in this direction. So by changing the current rapidly back and forth, I can rapidly change this magnetic field back and forth. It'll change directions. Now what happens if I put my pan on top of this coil? We'll say this is the handle of the pan. Now this magnetic field is going to have an effect on a magnetic pan. It's probably not too incorrect to think of the atoms in this pan as a bunch of little compasses. So as these atoms or groups of atoms in this magnetic pan encounter the magnetic field, they change orientation rapidly depending on how fast we change the magnetic field. And when they do that, energy is dissipated in this pan. So the energy in the magnetic field is transferred to the pan, and the pan itself is what does the heating. The pan gets hot and it causes the water to boil away or whatever is cooking. Now if you want to buy a pan for your induction stove, take a little magnet with you, like a refrigerator magnet, and if that sticks to the bottom of the pan, you're good to go. That's going to work fine. Another thing to look for is you want a flat surface on the bottom of the pan, so it'll be close to the surface of the induction stovetop, so you get very good coupling between the magnetic field and the iron pan.